A piece of insulated wire is shaped into a figure 8 as shown in the figure below. For simplicity, model the two halves of the figure 8 as circles. The radius of the upper circle is 4 centimeters and that of the lower circle is 8 centimeters. The wire has a uniform resistance per unit length of 5 ohms per meter. A uniform magnetic field is applied perpendicular to the plane of the two circles in the direction shown. The magnetic field is increasing at a constant rate of 2.4 teslas per second. Find the magnitude of the induced current in the wire, and find the direction of the induced current in the wire. Okay, so this is the diagram the picture gives us. We got a figure 8 here with a uniform magnetic field pointing into the picture. The first radius is 0.04 meters. The second radius is 0.08 meters. For the wire, the resistance per length is 5 ohms per meter, and the magnetic field is increasing at a rate of 2.4 teslas per second. And the problem asks us to determine the net current and direction of this current in the figure 8 of the wire. So first, we got to determine the voltage produced by the increasing magnetic field. And we got to use the equation epsilon is equal to negative n times d over dt of magnetic flux. Okay?
Yes.
And then magnetic flux is defined as the integral, the path integral of magnetic field dot dA. Okay? So, an n is the number of loops, but since I'm going to break each one up, it's going to be one loop, right? So that doesn't even matter. This can be summarized as the product of the magnetic field times the area. And since the area is staying the same, you don't need the d dt because it's staying constant. Simple enough. We have epsilon, or the voltage, is equal to negative the area times the rate of change of the magnetic field. Simple. Let's see the top part first. I label epsilon sub 1. The negative sign implies direction. We could throw that out for now. The area is pi times the radius squared. Again, dB dt is 2.4. Over here, we'll do epsilon 2. Luke, what's the area of a circle?
Circumference.
Pi r squared.
Okay.
Pi times the second radius is 0.08 meters. Again, times the same dB dt. Plugging this into your calculator yields a value of 0.012 volts for the first voltage, and for the second voltage, 0.048 volts. So that's great. We broke it up. We got two different voltages. And you might be thinking, let's just add them up. But no, that's wrong. You don't add them up.
You don't?
No. Because this voltage right here, we know that since it's the negative d phi dt, that since the magnetic field is increasing in this direction, nature's going to want to equilibrate itself and go this way. So this is actually going to have a current. This is going to want to have a current going this way. Same thing down here. The magnetic field's increasing in this direction, so we're going to want to go this direction. So this is going to have a current going in this direction. And you might think, oh, just add them up and we'll have a super big current, right? But if you follow this path, they butt heads with this one. And since this one's bigger and that one's smaller, this one actually takes over that one and makes it all go in one direction. Which means you can't just add them up. You have to subtract them. So the net voltage is going to be epsilon 2 minus epsilon 1, which is 0.036 volts. And that is not a backwards 33 loop. That's net epsilon. And that's great. Now we can just go over here, use our fancy equation. Epsilon is equal to IR, and epsilon over R is equal to I. But we don't know the R.
How do we find that out?
To find that out, we got to take the circumference of each loop.
I said circumference.
And multiply it by the resistance per unit length.
5.
So, we'll go over here. C1, what's the equation for circumference?
I don't know.
2 pi r.
2 pi?
2 pi times r1. And C2 is 2 pi r2. So the net circumference is equal to 2 pi times the sum of the radii, which is 0.012 meters. And this is equal to 0.754 meters. So that's great. And now we got to multiply 0.754 meters times 5 ohms per meter, which is the resistance, to get a net resistance of 3.8 ohms. And now that we know this and we know this, we just put them together in there. 0.036 over 3.8 ohms. This results in 0.01 amps. So that's the magnitude of the current in the loop. And like I said before, it's going to be going counterclockwise in the bottom loop and clockwise in the top loop. Yes?
How many volts or electricity is in the human body?
How many volts is in the human body?
Yeah, how much energy do we obtain?
I have absolutely no idea.
A lot.
Probably.
How much is in food?
Volts?
Yeah.
There's nothing.
There's none?
No.
That's carbohydrates.
No.
Yeah, there's carbohydrates in food.
Yeah, but there's no volts.
Well, I know, but like that, we get the power from carbohydrates.
Oh yeah.
I pay attention in science and math. That's pretty much it.
That's all you need. Alright, and then when I was first doing this problem, where I ran into difficulty was deciding what to do with the two different voltages. I first thought you'd add them up, because it's one piece of continuous wire, let's just add them up.
That's what I thought.
That's what he thought too. And then I realized that you couldn't do that because they're both trying to push currents in the different directions. So I realized we had to subtract them, because one on the bottom is really big, one on top small, one on the top gets eaten by the smaller one. Make sense?
789.
Yep. And then this shows my growth as a physics student because it shows that I understand Faraday's law and I'm able to apply it in more complex scenarios than just single loop structures. Any further questions?
No.
Okay.
I think so. No.
Thank you.